Okay, let's get right into it. We are constantly surrounded by these systems. Things working silently in the background, making our lives easier, safer, more efficient. Today, we're going to pull back the curtain on the invisible engine that really powers so much of our modern world: control systems.
So, let me ask you a question. What could a thermostat, a traffic light, and a washing machine possibly have in common? I mean, on the surface, they seem totally unrelated. One controls temperature, another directs the flow of traffic, and the last one, well, it just handles your laundry. But they all share a secret, a fundamental purpose.
And that's it, right there. The answer is control. Every single one has a specific job to do: maintain a certain temperature, manage how cars move through an intersection, or run that perfect wash cycle. They are all designed to exert control over a process to get a very specific result. And that brings us to the core idea here. A control system is basically the mechanism we build to make another system behave exactly the way we want it to. You can think of it as the brains of the whole operation. So, how do these brains actually work? Well, it turns out there are two very, very different approaches. So, let's start with the most basic type. This is kind of like Control Systems 101, the open loop system. Now, this system is pretty much a one-way street. You have an input that goes to a controller, which then sends a command, an actuating signal, to the thing it's controlling. Engineers call that thing the plant. And then the plant produces an output. That's it, story's over. The key thing to get here is that the output has absolutely no way of talking back to the input. Just think of this as the set it and forget it approach. A simple old school traffic light is the perfect example. It's just programmed to be red for 60 seconds and green for 60 seconds, and it's going to do that all day long, no matter what's actually happening on the road. The upside, well, it's simple and it's cheap, but the downside, it's dumb. It has no idea if there's a huge traffic jam in one direction and zero cars in the other. It just can't adapt. So that leads to a really critical question, right? How do you make a system smarter? How do you give it the ability to actually see the outcome of its own actions and then adjust based on what it sees? And the answer to that question lies in closing the loop. This is the breakthrough idea that makes pretty much all modern automation possible. Okay, now look at this diagram. Notice the huge addition here? That's the feedback loop. The output is actually measured and sent all the way back to the beginning. It then goes into what's called an error detector, which compares what we want to happen with what is actually happening. And the difference between those two? That's the error signal. And that's what the controller uses to make a much, much smarter decision. This table here really lays out the differences perfectly. Open loop systems, they have no feedback. Closed loop systems are built around feedback. And this is why open loop is often inaccurate, but cheap, and closed loop is way more accurate, but also more complex and, yeah, more expensive to design. And this is the crucial point right here. Feedback isn't just some nice little add-on. It is the single most important thing for improving a system's performance. It's literally what turns a simple machine into an intelligent one. Feedback is so important. Let's actually take a closer look at what it really does. This is the secret sauce. This is what makes everything work so well. So, feedback has four really profound effects on a system. It can alter its power or gain. It reduces how sensitive it is to changes. It affects its stability, and this one is huge. It helps cancel out unwanted noise. Let's dig a little deeper into two of the most powerful ones: sensitivity and noise. First up, sensitivity. So in an open loop system, if one little part starts to wear out or change just slightly, it can throw the entire output way off. But a closed loop system with that feedback is constantly checking its own work. So it automatically compensates for those little internal variations, which makes it way more robust and a whole lot more reliable. And, this isn't just a vague concept. Engineers actually have a formula for this. Now, you don't need to be a math expert to get the point here, but feedback reduces a system's sensitivity by this factor. All that means is the bigger that GH term on the bottom gets, the less sensitive the system becomes. It gets more stable. It's basically mathematical proof of just how powerful feedback really is. Next, let's talk about noise. Look at the left. That's our open loop system. Any kind of external disturbance or noise that gets in just gets passed right along to the output. There's nothing there to stop it. But now look at the diagram on the right. In the closed-loop system, that feedback path lets the system see the effect of the noise on the output, and then it creates a corrective action to cancel it out. It's brilliant. And the result is a system that actively fights back against noise.
Just like with sensitivity, feedback makes the output cleaner and so much more accurate than it would ever be otherwise. It's kind of like the difference between a fuzzy, static-filled radio signal and a crystal-clear digital broadcast. So, okay, let's zoom back out and put this all together. These concepts aren't just some abstract diagrams on a screen. They are literally running our world. So here's the bottom line. At their very core, control systems are either simple and inflexible open-loop systems, or they're these complex, intelligent, closed-loop systems. And the one magic ingredient that separates them is feedback. Feedback is what lets a system self-correct, and that makes it vastly more accurate, way more robust against changes, and just all around more stable in how it operates.
Think about it. The cruise control in your car, the autofocus on your camera, even your own body regulating its temperature, they are all closed-loop control systems. So the real question is, now that you know what to look for, what other invisible engines are you going to start seeing silently running your world?